So welcome everyone. Today's speaker is Gabriel Dima, who is a first-year ASP postdoc working here at HAO with Roberto Cassini on observations of neutral helium in the solar corona. Gabe obtained his PhD in 2017 from the University of Hawaii under the supervision of Jeff Kuhn, where he was interpreting spectral polarimetric observations of coronal emission lines obtained during eclipses and using the Solar C coronagraph. Before starting at HAO, Gabriel held a postdoc position with the National Solar Observatory, working on magnetic field diagnostics in the corona based on observations of forbidden magnetic dipole lines. And feel free to take it away when you're ready, Gabe.
Yep. Okay. Hi, everyone. Thank you for coming today. I assume everybody can see. I don't have any feedback, but from the cameras. But I assume I hope you can all see my screen and hear me clearly.
Yes, looks good. Thanks.
Okay, awesome. So thanks for coming today. I'm going to tell you a little bit about some work that I started doing as part of my PhD on very faint neutral helium emission from the solar corona. And I hope that I hope the title doesn't make it seem as if I solved the puzzle, because it's definitely still something that's still a little that's still confusing, and more observations are needed to really solve this. But I guess just looking at the title makes me think maybe I promised too much. So why look at helium, and what are some of the aspects that looking at helium that makes it a good diagnostic for studying the solar corona? So first of all, it's the second most abundant element after hydrogen. It has very strong resonantly scattered emission lines in the visible and infrared. And these can be observed from the ground. These scattered emission lines are polarimetrically sensitive to the magnetic field. This is through the Zeeman and the unsaturated Hanle effect. And why this is important will become a little clearer later. And furthermore, if you're looking at from the ground, if you're looking at the near infrared, these type of observations typically have an advantage over the visible because you have decreasing light backgrounds with wavelength. This is some data from a sounding rocket experiment. This is the Herschel experiment that was done in 2009. So SDO was not operating at the time. So the context images shown here are from EIT. The Herschel experiment, the Herschel rocket had three imagers on it, all narrowband and centered on the hydrogen and helium, on the hydrogen 1 Lyman alpha line and the helium 2 quote unquote Lyman alpha line at 30.4. And one of the main results from their field of view stretch from one of the main results is that the morphology of neutral hydrogen emission is different than the morphology of helium-2 emission. And this was interpreted as a variation in the abundance of helium in the corona near quiet solar time. So on the on the left here, you have hydrogen, the Lyman alpha, hydrogen Lyman alpha emission, and these two plots are actually both of the helium-2 line, and you can see that in the middle here, that near the equator, you tend to have this depleted region of emission. Because they were able to observe both helium and hydrogen, it was then possible to study what the latitudinal variation is of the helium abundance. And these are basically on the right here, you have these arcs, these arc-like cuts through these plots, showing solid, as the black lines are the hydrogen emission, whereas the red lines represent the helium abundance, and blue is the helium intensity. So you tend to have this very depleted helium abundance near the equator, around the equator regions. However, the abundance tends to increase around these regions where overplotted is also a potential magnetic field extrapolation for the day. So you tend to have helium appear to be concentrated more strongly near regions that have large expansion factors compared to regions where the expansion factors were lower. So the reason I'm showing this is because understanding how the helium abundance varies throughout the corona can help us model what the expected helium radiance is from the corona. Looking at an energy level diagram for the helium atom, for the neutral helium atom, because helium has neutral helium has 2 electrons, you have 2 different sets of energy levels, one for the singlet state, where the electrons have anti-aligned spin, and one for the triplet state. And looking at this diagram, a couple of things stand out. One of them is that the singlet state has the first resonance line is actually is in the ultraviolet, whereas for the metastable triplet level, the resonance line is in the infrared at 10A30, and then you also have this other resonance line, strong line, the D3 line at 5874. So why this is important is because in the ultraviolet, there's very little ultraviolet. There's much less ultraviolet light in the continuum than in the infrared. Than in the infrared continuum. So photoexcitation and photoionization photoexcitation plays a larger role in populating the triplet states than it does in populating the singlet states. Furthermore, a large source of exciting radiation that comes from the disk that excites the UV lines are actually from other helium-1 emission lines. So if you have like unusual shapes for the line profiles, this could lead to you have to, in order to interpret what you're seeing in the UV lines, you need to better understand what the shape of the spectrum is from the disk. Whereas in the infrared, usually you have the infrared has a much flatter exciting spectrum from the continuum radiation. In recently, or last year, Giulio Delzana and his collaborators put out a pretty involved collisional radiative model, which includes up to 300 levels for the atom, and a host of excitation and ionization processes to help better understand what kind of emission should we expect under coronal conditions. Temperatures around 1 megakelvin and electron densities around 10 to the 8. And I think this plot from their paper is a nice graphical representation of the effect of photoexcitation, of including photoexcitation in the collisional radiative models. So on the left here, you have what this is showing is the net rate brackets between each of the levels. So what's the total sum of up and down collisional and radiative excitations between the different levels? The orange represents transitions that are net collisional, and blue represents collisions that are net radiative. The dashed lines represent downward transitions, whereas solid represent upward transitions. So on the left, in the absence of an external in the absence of photoexcitation and photoionization, typically the populations are collisionally the population levels are dominated by radiative cascades after the ground state is ionized through collision. So you ionize the ground state, and then it recombines to these excited levels, and then the various rates sort of populate the excited levels. However, when you have an external radiation field here calculated at a radius of 1.05 solar radii, the effect is very large for the triplet state. Suddenly, primarily, all the population levels are dominated by radiative excitation due to the disk radiation. Using this model, Delzana and his collaborators were able to then provide some estimates for the line emissivities for helium-1 in the solar corona. So again, around 1 megakelvin. So this is a range of different transitions in the helium atom. On the left you have helium-10 middle is the D3 line, and then on the far right is the singlet transition, the 5804, the ultraviolet line. The top row, the emission line, the emission region is around so it's close to the limb, is only 0.05 solar radii from the limb, whereas the bottom is much further away. So the densities are also changed to reflect this. So for the top row, you're modeling densities around 10 to the 8 electron densities, and below around 10 to the 7. And the plot also includes a line emissivity for the iron-13 1080 line. So this is a moderately bright coronal emission line that has been observed pretty regularly from the ground. And you can see that the line emissivity for this line increases with temperature, and that's because the ionization of this line favors the ionization of iron-13. The ionization fraction of iron-13 peaks around log T of 6.15 or something like that. So this line increases at higher temperatures. Meanwhile, the helium lines tend to decrease with temperature. And when you include photoexcitation and photoionization, you tend to have around 1 megakelvin. You actually tend to have similar, or they predict similar line emissivities for 10-830 as the iron-13 line. And this is the case at both near and far solar radii, with actually at higher radii, the helium line has a slightly higher emissivity. Meanwhile, the D3 line tends to be, you'll notice here the different y-axes. So the D3 line is typically quite a bit fainter than the 10-830 line, and so it's unlikely. It's more likely to be seen in prominences or coronal rain or manifest or cooler or denser regions. finally, looking at the singlet line at 58.4 angstroms, it's clear that this line is almost 2 orders of magnitude fainter, has a lower line emissivity than both of these other triplet lines. Thus, sort of further further cementing this idea that the triplet transitions are some of the strongest that we can observe for neutral helium. I'd say one caveat, and they don't mention this in the paper, but one thing would be that the full width half maximum, so the line profile from line emission that was in equilibrium at this temperature, by my estimates, it would have to be a very broad line. It would have to be something on the order of 3.9 angstrom wide, which is significantly larger than anything than the helium line that's been observed so far. Another result from this study is the fact that the line emissivity of the helium-2 line, the 304, the 304 angstrom line, the one I was showing before from the rocket experiment, this line is about an order of magnitude brighter, and this is primarily because of the larger ionized fraction of helium plus found at coronal temperatures. This is a nice plot from a paper by Phil, where he's showing the impact of ionization fractions due to increasing temperatures. So you notice here that the helium plus tends to be a couple order of magnitude, has a higher fraction at these larger temperatures than the neutral helium line. And this pretty much is, yeah, although Phil used a different model for populating the atomic levels, I'm sure similar results hold for the Delzana study. So helium-2 is likely also a useful line for doing diagnostics. But because it's in the ultraviolet, it would have to be detected from space. So to try to get into a little bit why, how these triplet resonance transitions are affected by the magnetic field, we'd have to look at a zoomed in level diagram here. This is a triplet level diagram showing the first 5 terms of the metastable, first 5 terms of the triplet state, and also breaking down the sort of splitting the levels by their total angular momenta. And these kind of transitions between when J is greater than 0 or a half, then you have the possibility of polarizing the populations in the magnetic sublevels. So, for example, as the magnetic field is in the presence of magnetic field, the magnetic substates then become separating energy, and the coherences that exist between the levels become the levels become more decoherent. And as it turns out, for the helium transitions, the critical magnetic field at which the energy levels are split is comparable to the magnetic fields found in the solar corona. So between a few Gauss and 100 Gauss. So the 10830 line has critical magnetic fields around 1 Gauss, whereas the D3 line has a range. The various components of the D3 line have a range of critical field strengths, which are about an order of magnitude higher. So this makes it and the reason why this is important is when the magnetic field is comparable to these critical field strengths, the linear polarization of the line is sensitive to both the magnetic field strength and its orientation. Whereas for magnetic field strengths larger than about 10 times the critical field strength, you get into the saturated Hanley regime and you lose sensitivity to the magnetic field strength. So only the orientation then determines the linear polarization. So so this kind of sensitivity can then be leveraged to measure the vector magnetic field of the corona. So these are some examples of the type of studies or this is sort of like a small sample of the type of work that has been done to leverage these various polarimetric properties to measure the magnetic field in the corona. So a lot of work has been done on prominence magnetic fields. Interestingly, Veronique Baumier in the 80s did show that you could actually just use just linear polarization measurements of the 10830 and D3 line to devise a diagnostic for measuring the prominence magnetic field. One advantage to this is that you don't need the circular polarization. As detectors and technology got better, however, it became easier to get the full Stokes vector, and then more work came out where you could just use the full Stokes vector, because the Zeeman effect is sensitive to the field strength. So if you had both linear polarization, both unsaturated Hanley, or even saturated Hanley, and the Zeeman effect, you then have enough information to measure the vector field. Apart from prominences, this kind of diagnostics were applied to coronal rain. So coronal rain is a form of condensation where the plasma reaches chromospheric temperatures, and you have and the neutral helium fraction increases dramatically, enabling very fast Stokes observations to then capture the rain as it's falling. And finally, similar kind of work has been done on spicules. And all of these observations, though, kind of have something in common, and that is that they're primarily targeted at regions where the helium emission is very strong. And by that I mean, 10 to the minus 2 to 10 to the minus 3 of the disk intensity. And the reason I say this is very strong is because some observations taken by Jeff and his collaborators during the 1994 eclipse did seem to indicate that there might be a fainter helium-1 emission. That there seemed to be some, there may be a fainter helium-1 emission signature. And by faint, I mean on the order of 3 times 10 to the minus 7 of the disk intensity, which is a full 4 orders of magnitude fainter than prominence or coronal rain emission. And this kind of emission is very difficult to see outside of solar eclipses because of very large sky backgrounds. So in this particular experiment, you have a slit spectrograph that was oriented along this helmet stream, along the streamer, and this is the spatial direction, and this is the wavelength direction, and here you can clearly see the extended helium-1 glow when it's extracted from the 2D spectra, you have this sort of kind of persistent glow, even at very large elongations from the limb. So I guess I also just wanted to point out that even though this signal may seem, however, this signal is not necessarily the signal predicted by Delzana at all, because the line widths observed here were actually comparable to to cooler temperatures. So this isn't the same emission that they predict. Because of the extremely faint nature of this signal, it's difficult to obtain full Stokes polarimetry of it. Would be, I imagine it would be difficult to get the circular polarization measurements. Already, even linear polarization measurements are likely to be at the 10 to the minus 8 disk center level. Therefore, we tried to come up with an algorithm that doesn't rely on circular polarization at all and only depends on linear polarization. Again, inspired by the work done by Baumier et al. We actually propose using using a saturated Hanley emission line, something like a forbidden line, like iron 13 or silicon 10 in this particular work. And for example, these two lines, their critical field strength is on the order of 10 to the minus 4 Gauss. So they're firmly in the saturated regime for any magnetic field strength in the solar corona. So how such an algorithm would look like, you would take a linear polarization measurement of one of these saturated lines, and this would give you a theta m. So theta m is the linear polarization angle in this observing geometry. Z is the outward radial direction, and x is the direction along the line of sight. B is the magnetic field vector, and theta b and chi b are the inclination and azimuth in the sort of local radial frame of reference. And theta p is what I call the projected magnetic field onto the YZ plane. The YZ plane effectively is the plane perpendicular to the line of sight. So you have your measurement, your linear polarized measurement theta m, and because you know that you're in the saturated Hanley regime, that measurement can only really be parallel or perpendicular to the projected direction of the magnetic field. So this gives you two options for what the value of theta p is. So theta p is either minus theta m or minus theta m plus 90 degrees, so 90 degrees to it. As it turns out, this constraint basically generates a plane in which the possible magnetic field solutions can exist. So again, continuing with the same geometry here, you can imagine this plane perpendicular to the YZ plane. So the blue is perpendicular to Y and Z, to the YZ plane, and each of these vectors that I drew schematically then could potentially generate the same linear polarization signal that you measure. So this theta m, and conversely, there's another plane that is perpendicular to this one, sort of coming across here, but that's just not shown here. I'm just showing this particular one. So what you do is you come up with a set of values for the parallel and perpendicular cases for what the inclination and azimuth angles are for both, basically describing these two planes. And then taking these families of these families of angles together with a grid for the magnetic field strength between 0 and 5 Gauss, together with some estimate of the height for where the emission lies, and then feeding it into an atomic polarization code. In this case, we used Hazel at the time, or the instance of Hazel at the time. You can then produce Hanley diagrams of the possible solution sets. I forgot to mention that one of the assumptions for this for this particular case is that the emission, that we understand what the geometry of the emission is. So in this case, we took a geometry of emission in the plane of this in the plane of the sky, sort of cutting through the center of the sun, because that geometry then that geometry actually changes the shape of these diagrams. So it's important to understand the geometry, and that's yeah. So once you have these solution grids for what the possible polarization angle and amplitude are for the helium line, for these families of possible magnetic field vectors, you can sort of mark out the grids, and then sort of figure out where your measurement, which is the blue cross, intersects both of these grids. And this gives you a set of sort of four solutions that satisfy the two measurements that you have. Among these four solutions, the first two are actually give you the input magnetic field. I think, I haven't studied this yet, but I think if the geometry was not in the plane of the sky, it may be possible to break some of these degeneracies. So something like this applied to a different kind of geometry from away from the plane of the sky, you could have different degeneracies. So all right, it would be great if we could. It would be amazing if we could take observations of helium together with this other forbidden line, linear polarized observation with these lines, and then try to calculate try to invert for a magnetic field. Again, making very simple assumptions about about the fact that the emission is co-spatial, ignoring line of sight integration. So this is all still, I would say, pretty, in some ways, the best we can do, but a little bit unrealistic given everything we know now about the corona. But under those assumptions, in 2006, Jeff and his collaborators did try it again to measure the helium-1 signal. So they went to Libya, and they had with them a fiber-based IFU, linear spectropolarimeter. So each of these circles is sort of a representation of where the core of the fiber would be located, and then the central, this big circle here is actually the sun itself, and each of these fibers then gets fed into a linear spectropolarimeter, and it's a spectrum between 1 and 1.8 microns is obtained. So this way you can simultaneously get both iron-13, helium-1, and the silicon-10 line. What we found, though, unfortunately, for this particular experiment, the telescope was out of focus, and these large circles are meant to represent the radius of the size of defocus that was taking place. So unfortunately, I think a lot of the observations are a little bit confused by emission from a lot of this prominence material that's located on both limbs. So you can see more clearly in this image, you have quite strong emission here. I think that's H alpha, and both on both of the east and west limbs. So we measured helium in the fibers shown here. However, most of the time, the helium signal tended to have this varying trend. So, for example, on fiber 7 and 76, as the eclipse progressed, this is exposure number. As the eclipse progressed, you tended to have a decreasing signal, and to me, that would indicate that as the disk of the moon was slowly covering up emission from the prominence, that's why you're getting this decreasing signal. A couple of Fiber 86 did have a measurement that was potentially comparable to the 1994 eclipse, but because of these effects, it was I think difficult to draw any strong conclusions. So this is where we then, Jeff tried to look at it from outside of solar eclipses using this this coronagraph, the Solar Sea coronagraph. It's a half meter off-axis coronagraph, similar in certain ways to the Deacon's coronagraph, and it's a fiber-based IFU. It has 64 fibers, shown here sort of like schematically next to overplotted on a 174 image from AIA. Each of the fibers samples a region around 24 arc seconds in the corona, and the spectrograph is pretty high spectral, has decent spectral resolution, around 0.1 arc second sampling near the helium line. So each of the fibers basically gets re-imaged into a linear array, which then gets fed into the spectrograph, and this is that's what sort of the readout would look like. This is actually a printout. This is actually a plot of the Silicon 10 region. In previous incarnations of before my time with Solar Sea, they published two series of observations with Solar Sea of the helium signal. So one of them in 2007. Basically, they were only able to, because of the very large backgrounds and difficulty in calibrating the intensity, the detections were only made in linear polarization, because linear polarization is a difference in technique. Your variations in your flat field are not as severe as when you're looking at the intensity. So you can it's actually easier to see very faint signals in linear polarization and then in the intensity. So one of these studies in 2010 was able to establish a kind of a weak correlation between the polarized brightness for helium 10A30 and the presence of streamers. So white light, using white light as a proxy for streamers, or as white light increases, you tended to have a slight increase in the strength of the polarized brightness of the helium detected. Also in this paper, a different hypothesis was put forward for where this emission originates, and I call this the dust hypothesis. The idea is outside of some dust-free zone, which is at present still unknown, just how close the dust gets, it's not clear yet where the inner radius of this dust-free zone is, but basically the presence of this dust causes neutral helium to be produced on the surface of the dust grains from absorbed solar wind, ionized helium in the solar wind. So the helium gets absorbed on the dust, neutralizes, and then is deabsorbed, and then scatters this radiation towards us. Because of that, only along a particular line of sight, only emission, the emission sort of is not coming from this plane, but rather is coming from planes behind and in front of the sun. But they came up with a model to try to predict what the intensity would be if you were to observe at an elongation of about 1.4 solar radii, and then you progressively shrunk the inner radius of this dust-free zone, and you can get something similar in brightness for as what was observed during the 1994 eclipse. So if the inner radius was around 2 solar radii, then using this model you could produce something along those lines. The one advantage of this model versus the population of helium in thermal equilibrium with the corona is that with the electrons with a 1,000,000-degree corona is that this model doesn't predict overly broad emission lines. This model actually predicts narrow emission lines, which are more consistent with the observed emission lines. So after all of that, my goal during my PhD was to try to use SolarC again with a new configuration to try to take more of these observations, try to more clearly establish the link potentially between helium and increased white light emission. And I tried this. However, it's not clear yet. I'm still trying to interpret the data. This is one example of one of my observations. So this is a 2016 observation on the east limb, and here you can see the red square shows the field of view of the fibers. The blue lines represent the linear polarization orientation measured for helium, and basically here you have a two-dimensional spectra of all the fibers. So you can clearly, after they've been corrected for crosstalk and had the continuum removed. So you can see this is sort of the helium line appearing in Stokes Q in Stokes Q U and very faintly in Q. To increase signal to noise, we actually binned all the fibers inside these dotted lines represent 0.05 solar radii wide bin. So we bin the signal from all the fibers inside these regions to try to boost the signal to noise enough to actually measure the linear polarization. And this is what the plot here on the bottom right is showing. That's Stokes I, Q, and U for these different radial bins. So each color corresponds to a different radial bin. I can tell you from memory that blue corresponds to the innermost radial bin, and then it progressively, actually, the line gets weaker. And this radial plot sort of shows that. So this is the measured polarized intensity at the peak, measured in disk units. So as it turns out, assuming my calibrations are correct for and that's a whole different lecture. That's a whole different talk on whether whether the calibration works or not. Actually the polarized intensities are a good order of magnitude larger than what was originally observed in 2010. So this was on the order of 10 to the minus 8, whereas these new observations tend to be closer to 10 to the minus 7. And that's just polarized light. Another interesting aspect of these measurements is actually that the forward half maximum of the lines tends to be almost double the forward half maximum of the scattered light in the Stokes I component. So it's a lot more. It's more difficult to see Stokes I because of the very large backgrounds. If you look at the scale here, we're talking, it's it's like 100 millions, whereas the polarized signal is on the order of 0.2 millions. So it really, the scatter light really drowns out the spectrum, but you can still see a very, a sort of an absorption line that is basically disk light scattered into the field of view by the sky and by the mirror. However, the line width of this feature tends to be about half of the line width of the measured polarized signal. Thus, making it a little bit not clear whether the two are related or not. So this is another measurement on the west. This is another example of a measurement on the west limb. In this case, the linear polarization is no longer whereas on the east limb measurement, the linear polarization tended to be more tangential to the limb, as you would expect from a permitted line. On the west limb, it's less tangential. Well, it's not really. It's definitely inclined. And I'm still, whether or not this is an artifact, I'm still trying to determine. I don't have a plot now of what the continuum polarization is doing, and I think that would give me a better idea of whether this is again crosstalk or an artifact, improper crosstalk removal or some other artifact. But again, you have pretty strong. You have pretty strong intensities for this polarized observation. So this is still kind of ongoing work that I'd hoped to. I had wanted to get more done for this presentation, but in the end, other things interceded. So this is so far the closest I've gotten. Another way to tell if the signal is really just scattered linearly polarized chromospheric light is to look for the presence of the blue component of the triplet. The blue component of the triplet originates from a J. Originates from a J equals 0 to J equals 1 level. So because the upper level is J equals 0, it has no magnetic substate, so therefore cannot be polarized. Therefore, a linearly polarized observation off the limb would then indicate more of a scattered light, because in absorption, the blue component is polarized because it actually goes in reverse. It goes from J equals 1 to J equals 0. So as shown here in this example of a measurement on disk filament, you get a pretty clear linear polarization signal in the blue component. And the data that we have, the signal to noise, even with the binning, does seem to show some slight emission in the blue component, but it's not. I wouldn't. It's difficult. It's difficult to say for sure. So this is on the right here. I actually smoothed the spectra with a Gaussian to try to kind of cut out some of the noise, and you end up with this. You end up with a slight bump where the blue component would be. So, yeah, it's still a little inconclusive. Of course, the discrepancy between the line widths is puzzling, because if this was scattered light, why wouldn't you would expect it to have similar a similar line width, but it doesn't. So basically, looking forward, the hope is that DKIST, once it finally starts taking measurements, will actually help with a lot of the problems that we've been battling with the smaller size telescopes. And it does this because it has a very large primary mirror, so you can collect a lot more signal. You have some measures in place to reduce scattered light from the mirror. Fundamentally, it is on halakala, so you have the sky backgrounds are low, on the order of the hope is that we can get down to 25 millionths, and all of these factors combine to allow us to then try to target these 10 to the minus 8 or 10 to the minus 7 signals. So for the first for cycle 1, the operations commissioning phase, we proposed a series of observations, mainly to try to reobserve the line. So we proposed a series of observations with CryoNersp, which is a slit-based spectropolarimeter. Basically arranging the slit at these 6 positions around the limb to try to get an idea of what the distribution would be of the signal, and then try to really actually just measure the absolute calibrated intensity. So try to do a better job at measuring both polarization and measuring the intensity of the line, if indeed it does exist. And in the future, assuming the observations go well and there is a signal, potentially trying to look at more coordinated observations of helium with another forbidden line. This could be done either with cryoNIRS. The only problem with cryoNIRS is that you have to cycle through the lines, whereas a spectropolarimeter like DLNIRS, although it has a slightly lower throughput, it does offer the ability to simultaneously measure, at least in 2 of the arms, you can measure the helium-9 and potentially the silicon-10 line. So in summary, I hope I convinced you that helium is an interesting element to study, and that it has a number of transitions that are polarimetrically sensitive and could be of use to studying the coronal magnetic field. There's still, the problem still exists as to where as to whether there is a pervasive faint diffuse helium-1 signal in the corona. I would say those images in 304 from the sounding rocket give me hope that we'll be able to see a signal. And finally, yeah, DKIS will offer the kind of stability that we need for this kind of very faint observations. Thank you very much.
Thank you, Gabe. Does anyone have any questions? You know, this business of a possible signal of the 10-830 higher in the atmosphere than you might expect is also something that was observed in the 2017 eclipse in an experiment we had in Wyoming.
Right.
Maybe you've seen that paper, or maybe you've spoken to Phil about it, but I don't know if it's related to what you're talking about here, or if it's a...
I haven't. I think I'm aware of that paper, but I haven't read it yet because I'm kind of bad with that. But I will definitely have a look at it, and if Phil could probably tell us about it. I see him and Joe.
Yeah, Phil has his hand up just now. Do you want to ask something, Phil?
I'm not sure who was first. Sorry, you're the moderator.
Sure, yeah. Thanks for the talk. What I like about this kind of talk is you're presenting unsolved puzzles and not going through the sort of NASA approach, which is to try and validate things in science as opposed to invalidate them. So I really like this sort of refreshing sort of presentation of something that isn't solved yet. I don't want to comment on the previous paper. I wasn't listening completely clearly just then. But I did want to point out that I find the difference in the line profiles themselves between what you'd expect from, helium particles that are in equilibrium with the local electron temperature to be really striking. I mean, this is an important thing. And I just looked in some notes I've got here, and at least the proton-electron equilibration time is about a minute in the corona, around in the low corona, the quiet sun, something like that. So it's going to be a bit longer for helium because unequal weights particles or mass particles colliding don't exchange so much energy per impact. So it's going to be a few minutes to do that. But nevertheless, I think what it's telling me is if you're observing these narrow lines and it's really there up in the corona, that the helium can't originate from recombination like like is in the model that Delzana et al. Proposed, because that model, the velocity of the charged ions, then when you impact that with an electron, that velocity is unchanged, and so it remembers its temperature in terms of a thermal distribution function, and it's going to be a very broad line. So it's a real puzzle, and I think you should definitely, pursue this ad nauseam and really get to the bottom of it, because there's something really funny going on here. And as Jeff has been pursuing this, he has a nose for very interesting but hellishly difficult problems, and you're a brave guy to go after this one, I think. So anyway, that's the only comment I really wanted to make.
Yeah, no worries. Yeah, like I said, I hope I'd like to see a more clear example of the signal first before. Yeah, there's just been a lot of attempts to reobserve it, and I can't say for sure that I've been convinced. They all have different, trying to do an absolute calibration has been difficult, and of the signal. So there hasn't been like a clear example of this, unless the 2017 eclipse that Paul was mentioning shows something similar. But I imagine you would say I have to look at that. I have to look at those results. So yeah, my literature research is, as usual, is not great. But yeah, let's see. I guess the hope is that we'll get a more clear idea once DKIST takes these observations.
Okay, Joan?
Yeah, hi. Thank you for the talk. I have a question. You had some sort of hypothesis there about, you had an hypothesis there about possible dust-free area, and that there'd be some scattering outside of there from a dust zone.
Yeah.
I think you were speculating that you needed about 2 solar radii outside of that, where there's dust, to match the eclipse observations that Jeff had. That seems awfully close to the sun. I'm just wondering if you're planning on using some of the dust measurements from Parker, because Parker Solar Probe is observing dust as it moves in, and would you be keeping track of that to see where maybe they detect the dust-free zone as they get closer into the corona?
Yeah, that's a really good point. I've wanted to look more closely at Parker data, but I haven't had a chance to look at it. Yet. Also, I think perihelion, or the closest approach for Parker, is 16 solar radii. Is that correct?
I think it's about 9. But
9?
there's some speculation even at 9 it might already be dust free. So
I think
it's an interesting thing to keep an eye on.
Of course, there's also the question though of and this is again jumping into an entirely different field of research that I'm not an expert in. But there's all the question is how small can the dust be before Parker measures it? Like there's this. I wonder if Parker has a cutoff in the dust size that it can measure. So even though it may measure something that seems dust free, maybe it's just dust free past a certain grain size.
Yeah, that I don't know.
So there's kind of possibilities, but of course, I mean, if Parker finds that there's practically no dust at those very high radii, then absolutely this may not make this hypothesis may not make as much sense. There's also, I think, once we take linear polarized measurements of the helium, if we can measure it, that may also tell us a little bit about if it's coming from near the sun or far away, because if it's very far from the sun, where the magnetic field is very small, then you also don't actually see any of the Hanley effect. So you'll measure linear polarization perfectly tangentially polarized to the solar limb. So the hope is that maybe that'll offer some solutions. And helium as a diagnostic is only useful. It's kind of only useful from that point of view if there is a deviation. If there are no, if it's all perfectly tangential, like a halo, which could come from, which is what it would look like if it comes from the dust, then it would be bad because, but maybe that will tell us more about where it's originating from.
Thank you.
No worries. Thanks for the question.
Okay, thanks. Are there any more questions before we wrap up? If not, then thank you again, and thanks everyone for coming.
Thank you for listening, everyone. Have a nice day.
Thanks.
Paul.